All right, let's dive into a real head-scratcher at the heart of modern car safety. Our cars are getting smarter every single day, right? They're loaded with all these amazing sensors and supercomputers. So why on earth do they still get into accidents for reasons that have nothing to do with a broken part? Well, let's unlock that secret.
I mean, it really does sound like a riddle, doesn't it? If all the hardware is working just fine and the software is running exactly the way it was designed to, how can a car just suddenly do something dangerous? This is the big mystery we're going to solve today.
So picture this. You're just cruising down the highway, the weather's perfect, there's nobody in front of you. And then, bam! The emergency brakes just slam on, throwing you against your seatbelt. You look down at the dashboard, no warning lights, no error messages. As far as your car is concerned, it just saved your life. But from what? This isn't a malfunction. It's a crazy phenomenon called phantom braking, and it is the perfect example of this whole new kind of risk.
To really get why this happens, we need to talk about this massive shift in how we even think about safety. You see, the old way of just looking for broken parts, it just doesn't cut it anymore. We've gone from worrying about a faulty piece of equipment to questioning the car's entire recipe.
Think of it like this. The old safety standard, ISO 26262, was all about malfunctioning behavior. It basically asked, okay, what happens if a part fails? But this new standard, SOTIF, it asks a totally different question. It focuses on something called functional insufficiency, which is all about what happens when a perfectly working system just isn't smart enough for a really complex, real-world situation.
And this slide really lays out that difference. On the left, you've got the old way, functional safety. It assumes the recipe is perfect and a component breaks. But on the right, you have SOTIF. It assumes the components are perfect, but the recipe itself, the design, has limits. And so the goal completely changes, from just preventing failures to actively managing the chaos and uncertainty of the real world.
And that brings us right to this core idea, functional insufficiency. It's the official name for that gap, the space between what we told the car to do in its programming and the messy, unpredictable, infinitely complicated reality of just being on the road. And it's right inside that gap where these new dangers are born.
Okay, so let's put this new way of thinking into practice. Let's go back to our phantom braking mystery and use this SOTIF framework almost like a detective's toolkit to see exactly how a perfectly working car can do something so startlingly dangerous.
SOTIF gives us this thing called a chain of events. Just think of it like a series of dominoes falling. It shows how a totally normal situation can escalate into a full-blown accident. It kicks off with a triggering condition, which then exposes a functional insufficiency. That leads to hazardous behavior, which creates a hazard. If a person is in the wrong place at the wrong time, you get a hazardous event, and that can lead to harm. We're going to break down those first three steps right now.
So the first link in that chain is the triggering condition. Now, it's super important to get this. This is not a system failure. It's a completely normal thing that happens in the outside world. Like heavy rain, a crazy sun glare, or even a confusing road sign that just happens to be the one thing the car's system doesn't quite know how to handle.
So, in our phantom brake scenario, the trigger was simply the highway overpass. To the car's radar, that huge metal structure hanging over the road can create a signal that looks almost identical to a gigantic truck that's just stopped dead in your lane.
And that trigger, it immediately exposes the second link in the chain, the functional insufficiency. This is the system's built-in blind spot. Remember, it isn't broken, it just has a limitation in what it's capable of doing.
The insufficiency here is actually a physical limitation. Most car radar systems are awesome at seeing things from left to right, but they have really poor vertical resolution. That means they literally can't tell the difference in height between an overpass 50 feet in the air and a truck's tailgate 5 feet away. That ambiguity, that's the real problem. And because this system can't tell the difference, it leads us to the third link, hazardous behavior. This is the moment where the car's internal confusion turns into a real physical action out on the road.
And this part is just fascinating because it shows you the car's dilemma. The computer gets this signal. It asks, is this a harmless overpass or is it a dangerous truck? It can't be 100% sure. So what does its logic do? It defaults to the safest bet, slam on the brakes. It's the wrong decision, of course, but it's a totally logical one based on that system's limited ability to truly see the world.
Okay, so up to this point, we've only been talking about the car and the environment. But SOTIF forces engineers to factor in the most wild, most unpredictable variable in the entire equation, us, the drivers.
SOTF is smart about this. It splits our potential screw-ups into two main types,
On one hand, you have direct misuse. That's when you're intentionally trying to fool the system, like wedging a water bottle in the steering wheel to make it think your hands are there. But then there's indirect misuse, which is way more subtle and honestly a lot more common. That's when we simply trust the system too much. And this is where things get really, really dangerous. Look, a phantom braking event on a totally empty road is just an annoyance. But what if it happens when a driver has gotten so comfortable, so trusting of their car, that they're busy texting or just completely zoned out? This is what experts call the out-of-the-loop problem. When we let the car do all the work, our brain kind of checks out. We lose what's called situational awareness. So, when that system suddenly panics and needs us to take over, our reaction time is way, way slower. An accident that should have been avoidable can suddenly become unavoidable, just because our brain wasn't ready to jump back in. All of this, it leads us to a really fundamental, almost philosophical question for automakers. If a perfect, flawless system is literally impossible because the real world is just infinitely complex, how in the world do they decide when a car is actually safe enough to sell to us?
Well, engineers use a few key principles to draw a line in the sand and define what acceptable risk even is. One is basically that the new system just has to be statistically safer than a human driver. Another says the risk should be just a tiny fraction of other risks we all accept in daily life. And a third, known as ALARP, or as low as reasonably practicable, is a pretty pragmatic approach. You make the system as safe as you possibly can until the huge cost of making it even a tiny bit safer just isn't worth the small benefit.
Ultimately, what SOTIF really teaches us is that chasing after a perfect car might actually be the wrong goal. The real challenge, the real genius, is in designing a car that understands its own limits and, when it inevitably gets something wrong, is built to fail safely. It's a huge shift from chasing perfection to managing imperfection. And how we all navigate that challenge, well, that's going to define the future of our relationship with the very machines we trust with our lives.